So students, welcome to video class 25, and we are into the last part of the root locus, that's part 4. Okay, so today we are going to do one more problem which is quite different from the two problems that we studied. So I think it's the third question number 3. Okay. Okay, now here is a question for you. The open loop transfer function is given by g as hs is equal to k by s into s plus 6 into s squared plus 4s plus 30. Sketch the root locus and comment on the system stability. As I mentioned, this is quite a different problem. So let's start with step 1. What is step 1? In step 1, you need to identify the open loop poles. Identify the open loop poles, right? Now for that you should equate the denominator of the given g of s to 0. So equating that, you will get s can be 0, or s can be minus 6, right? Or this s squared plus 4s plus 13, when you factorize that, you will get the factors as minus 2 plus j3, and if there is a minus 2 plus j3, as I told you earlier, that always the poles, complex poles, this is a complex pole, and complex pole occurs in pairs. That means you must have a minus 2 minus j3. Okay, so these are the poles. Now what is the difference between the first step itself? We can see the difference between the previous problems that we did. So far we have considered only the real poles. Now this is the first time we are considering the complex poles. Okay, now let us see. So when you consider complex poles, so far we have studied about 8 steps in the procedure of the root locus. Now 2 more steps will be required for catering this type of complex poles that we will see as we develop, as we go further. Okay, so this is the step 1. Now what is the step 2? The step 2 is about the termination of the root locus. Okay, now before that you need, okay, so once you identify the open loop poles, you are to plot the pole 0 plot, or have the pole 0 plot in the S plane, okay, as shown. Okay, so here is a pole 0 plot for you. So one resides at s is equal to 0, the other one resides at s is equal to minus 6. Then you have one as minus 2, so this coordinates is minus 2 comma plus j3, so this will be minus 2 minus j3 is the coordinate of this point. So these are the 4 poles. Now what can you say about the termination of root locus? This is another step you should include in it. So you should have an idea before proceeding how this root locus terminates. So we know that you have only 4 root locus, 4 poles in this S plane. That means the root locus we have studied from the two problems that we did, that the root locus always starts from this open loop poles, right? So since there are 4 poles, you can see that no zeros nearby. You can say that all the 4, the root locus starts from the open loop poles but terminates at infinity, and we do not know how it goes to each infinities, whether it is going to the positive infinity or the negative infinity on the left half or on the right half. That we do not know by this step, but we can say that it root locus, all the root locus terminates at infinity. Why? Because there are no zeros nearby these poles. Okay, Now, what's your step 3? Now, the step 3 is to find the number of root locus branch. Okay, number of root locus branch. Now, you can find out the number. So, the P, that is the number of poles, P is equal to 4, Z is equal to 0, number of zeros. So, obviously, P is greater than Z. Therefore, the number of root locus branch is equal to 4. So you have 4 root loci. Okay. So next one is, that's your step 4. Step 4 is about the existence of the root locus on the existence on of the root locus on the real axis. That's the next step. So again, coming to this graph, so you must say that between each pole. So the along the real axis, towards the right of the pole s is equal to 0, there is no root locus. Why? Because if you count the number of poles and zeros after this point, that's going to be equal to 0. Therefore, the number of poles is an even number. Therefore, no root locus exists in between. So I'm just drawing that by so this shows that this red or this maroon line shows that it is not having any root locus over here. Okay, now next point is coming to this point, this side, that is between 0 and -2, because at -2 you have again 2 poles. So what about the root locus? Is there any root locus? So you need to write a statement. So you need to write, I'm not going to write it. You need to write from the as a statement, that is towards the right, as shown in the graph. This is how you should write. On the real axis there is no root locus, because you should specify the reason, because the total number of poles and zeros towards the right is equal to 0. Now between the points -2 and 0, now between the point -2 and 0, because there happened to be another pole at -2, therefore before this, if you count the total number of poles and zeros, you can see that this is an odd number. So that means this particular location, that is from -2 to +2, you have what? You have again a root locus. Now just go towards -3. Look at that -3. Now from this -3, if you count the number of poles and zeros towards the right, you can see again this is an odd number, right? 1, 2, 3. That means there also exists root locus over here up to this point, right? Up to this point. Because till this point, if you count the total number of poles towards the right, is again odd. Now coming to this area. Okay, so as we done in the previous problem, you may believe that there will be some root locus. No, you don't have any root locus over here. Why? The reason is there is no root locus over here. The reason is, if you count the number of poles towards the right of this is 1, 2, 3 and 4, which is an even number, so no root locus present. So here is no root locus, there is root locus here, there is root locus here, no root locus here. So this is how you need to specify this as points, right? You need to write like this: from 0 towards the positive, there is no root locus. Reason, you need to specify the reason. Now from between 0 and -2, there is root locus. Between -2 and -6, there is root locus on the real axis. You must specify on the real axis. Then beyond the point -6, there is no root locus. Every time you need to specify the reason. That is your step 4. So you need to write, I'm just specifying it, you need to write it as a statement over here. So that is step 4. Now coming to step 5. Okay, now to step 5. Step 5, we need to so far we have studied only real poles. Now in this problem, as I told you, you have a complex pole. Now for the meantime, I'm just drawing as if it has got only some real poles. I'm not considering these complex poles. Let it be there. We'll consider that later. just draw, uh, I mean, till the step 7, you need to go in such a way that you need to do this in such a way that you have only some real poles. Okay, so that's your step 5. Now what's the need of step 5? We know that, see, so as I told you, so you don't have to consider this, but you need to be, the concern is of these two poles. Now we know that since all this area, we have already proved that throughout this area there is root locus. That means we will be forced to believe that this will move in this direction, this will move in this direction. So some way or other, at a particular point, that will meet. Okay, and that means that results in the 5th step, which is the breakaway point. Okay, breakaway point. Now how to find out the breakaway point? You need to find out from the characteristic equation, from the characteristic, this is GSHS, right? Now this is open loop transfer function. From this open loop transfer function you can find out the characteristic equation, and the characteristic equation is 1 plus k by s into s plus 6 into s squared plus 4s plus 30 is equal to 0, or you can say that that is equal to s raised to 4. So you just take the LCM, and when you equate, you can write like this: s raised to 4 plus, okay, s raised to 4 plus 10s cube plus 7s3 37s square plus 78s plus k is equal to 0. Okay, right? So you may just do it by yourself to find out the scalar. So it is simple. You need to take the LCM so that this whole term comes over here, and that plus k can be equated to 0. That's your characteristic equation. So expand this and try to see that whether you are getting this answer. That is the characteristic equation. Now what will you do? From this you need to find out your k. Now what is your k? K is nothing but it is minus of the whole thing, right? Minus of s raised to 4 plus 10s cube plus 37s square plus 78s. Okay, you must make sure that these coefficients are the right. So that's why I told you must do it by yourself. Okay, so just check whether the answer is the same or not. Now, how will you find out the breakaway point? Now, I am again explaining the breakaway point is a point. So, this moves because, so as I told you earlier, this is the point at k is equal to 0. This is again a point at k is equal to 0. This is again a point. So, you have 4 points corresponding to k is equal to 0, right? Because there are 4 poles. So, obviously, the root locus starts at the point when k is equal to 0. Now, as you vary your k, for the meantime, you are forgetting these two. As it varies, what happens is k varies in this direction. These roots moves in this direction. This one moves in this direction, and at a particular k, you can see that meets together. So that will be the maximum value of k on the real axis. So definitely, you can find out dk by ds and equate to 0 and get the condition for this, and that is the location or the point at which this meets together, or that point is called as a breakaway point. Okay, now you can differentiate this k with respect to s. Differentiating that, you will get this as minus 4s cube, right, plus 30s square plus 74s plus 78, and that is to be equated to 0. Okay, so that you can see that this is a, okay, this minus sign will get cancelled. So this is 4s cube plus 30s square plus 74s plus 78 is equal to 0. So this is actually your dk by ds, and you can solve this so as to get the condition for this for the breakaway point. Okay, now how to solve this? You can either use your calculator to solve this anyway, you know that this equation is a third order equation. So definitely you will be having some s1, say some s2 and s3. Okay. Now there can be different points, but we'll be only selecting the points that comes in between 0 and -6, because the breakaway point, our need is, we need a breakaway point that comes in between 0 and -6. Now, at times you may be finding very difficult to solve such expressions if it may go beyond this orders, higher orders. Even I think even from your from your permitted calculators in your university exam, it may be difficult to solve higher order polynomials. Now, I think you can solve this by using your calculator. Anyway, now if you cannot, there can be. So let me write the answer. So our breakaway point is going to be equal to, our breakaway point is actually equal to minus 4.2. Okay, this is 4.2. This is your breakaway point, or this is the breakaway point. Breakaway point. Okay, now I'll just explain. If your calculator is not capable of solving this, you can solve this by simple graphical approach. Say you can put some real values to s. So okay, you can put some 0. So when you put 0, this is going to be what's the value of this? So you can call this function as f of s. So what you're going to do is you're going to plot this f of s, okay, f of s, for some of the real values of this s. You will be putting some values between 0 and -6 to this equation, and you can plot. Now just put s is equal to 0. S is equal to 0 means you're getting 78. So f of s is going to be a higher value. So you don't have to bother about any points near this. Okay, so this is just an arbitrary, so you may just find out for the meantime, just find out f of -5 and f of -4. Okay, now when you substitute f of -5, you're going to get this as -42. F of -4, when you equate, you will be getting +6. So look at this, at -4 this is going to be +6, right? So these are 2 points, so that means 5. So this will be 6 at -4, right? At -4 it will be 6. So this is the point, right? So this is the point corresponding to -4. -4, you will be having f of 5 is equal to plus f of -4 is equal to 6. Now what about the f of -5? F of -5 is, when you plot f of -5, you'll be getting this as 42, right? 40, yeah, it comes around -42. So okay, if you plot here, it will be -20, -25, okay, -25, -30, and it goes on like that, 35. Okay, so let's find some other points other than so it's too big for this graph. So I'm going to find one more point. I mean, little closer to -4. Okay. So you can see that at f of -4.5, that is at 4.5 is this, -4.5 is this. So at -4.5, this becomes a negative value. So this will be, right, 10. Okay, this is 5 each, right? Yeah. So this is 10. Okay. So 3. Now this is 10. That means it is -12. So 1, 2. That is a 4 divisions, right? So that will be so that is at -4.5. So this is the point at -4.5, right? Okay. Now if you can join this, okay, join this you can find out the point which crosses this 0 axis. This is your 0 axis, right? Now you can find that to be 4.2, right? This is actually 4.2. Okay, so this is how you can find. So that, what's the meaning of this? This f of s is having many values, and f of s will be crossing at this point, over this point, and there can be another points that can be positive or anything values greater than all these things. Okay, so this is how you can find out if there is any difficulty in evaluating. So f of s, somewhere or other you need to equate this f of s to 0. So this is one of the points by at which this characteristic equation or this condition gets satisfied, that is dk by ds becomes equal to 0 at s is equal to minus 4.2. So coming back to our graph, so what's your so this is your 4.12. so this must be your breakaway point. Okay, now once you found out your breakaway point, what's the next issue? So do remember, we are just ignoring this for the meantime, this complex pulse. So this is how it is. This pulse moves a bit faster and reaches over here. Now this pulse is a bit slower. Okay, so this has to cross only this much distance, while this one moves in a faster way. So this pulse moves in a faster way. This one comes at meet at this point. Now the problem is whether this one of the poles, if this pole moves in this direction, definitely the other one moves in this way. If this moves vertically up, then it will be moving vertically down. If it moves towards the left side, then this will also move the left in the mirror, exactly in the path of its mirror image. Okay, so that's the dilemma that we are into. Now how to solve this? So in order to that, that's your step 6, right? Now what is your step 6? Step 6 and step 7 are for the asymptote, and I tell you again, asymptote is not a part of the root locus. Asymptote always guides the root locus. So asymptotes are drawn to find out the direction of the root locus. Now how to find out the asymptote? Now in order to find the asymptote, you require two things, and in the step 6 you will be finding out the angle of asymptote. And the angle of asymptote can be, I'm not going to explain that because we have already done that. So the angle of asymptote can be found out as, okay, so this is it, theta. So you have theta k is 2k plus 1 into 180 by p minus z. We know that p minus z is 4. So k varies from 0 to p minus z minus 1, that is 0 to 3. So you have 4 options. So 4 angles corresponding. When you substitute each values of k, you will be getting theta 1, theta 2, theta 3 and theta 4. Okay. Now how to plot this theta? Now if you want to plot this, you need to have another idea about the center of gravity, or that's your step 7, or the meeting place of the asymptote on the real axis, or the intersection point of asymptote on the real axis, or that is called as the center of gravity. Okay, so you are going to find out that. And what is that? So you will denote that by x. It is equal to sigma poles minus sigma zeros by p minus z. So you can simply just sum all the poles. Sigma poles means you need to include all the poles, whether it is complex or whatever it is, you need to add all these. So, in effect, it is actually adding the real axis. I mean, why? Because when you add these two, this imaginary term gets cancelled. So effectively, it is nothing but it is just the addition of the real term. So it is 0 minus 6 minus 2 minus 2. So this will be equal to 10, right? So this will be equal to minus 10 divided by 4, or this is equal to minus 2.5. So this is it. So the intersection point of the asymptote is minus 2.5, and these are the angles. Using these steps, using these two steps, you can plot, you can find out the you can draw this asymptote. Okay. Now look at this. Here you have the point minus 2.5. This is the point minus 2.5, or you will call this as the center of gravity. Okay. Now look at this. Now in this case, again, as we did in the the previous problem, the center of gravity is a point different from the breakaway point. Okay. Now using this center of gravity, you need to draw the asymptote at the angle 45, 135, 225, and 315. So one, I will be showing you how to find out this. So place your protractor over at this point. Okay, you must be very careful in doing that. So this is your 45 degree, right? This is up. So this is plus 45. That means it is the anti-clockwise direction. So join that. Okay, join these 2 points. Okay, so always use this is your center of gravity point. Always use dotted lines. The hard lines are always for root locus. I told you that this is not a part of root locus. This is just a direction. So mark this angle as 45 degree. Okay. Now similarly you can draw the rest of the angles. So the rest of the angles will be drawn as. Okay, so this is how it is. This is 45, this is 135. Now, this is actually, you're keeping this protractor here, and you can find out the 45 from this, that is 225. From this, if you plot the 45, you will get this 315 degree. Okay, so this is it. Now, you have got an idea how this root locus is going to move. Now, still, there is again a problem. So it is showing 4 directions, and we know that this has got 4 poles. So definitely this asymptote will be a directive element, it will be showing a direction for each of the root locus that starts from each poles. Okay. Now the question is how this can move. See, this particular pole can move in this way, right? This can also move in this way. And similarly, the problem gets a bit more confused how it is going to be. How is it possible? Okay. Now, for that, what must be the next step? Okay. Now look at this. How to solve such things? Now we know that the breakaway point, look at this. What is the breakaway point? Breakaway point is minus 4, right? So that means this pole will be reaching at any cost, this will be reaching at this point, right? Minus 4. And this pole will be reaching over here. So that means these two asymptote has nothing to do with the pole coming over this place, right? These two asymptote cannot give the direction of this, because this is actually all the points that comes about here, that only can be that's direction can only be dictated by these two asymptote. So that means from this you come to a conclusion that this particular asymptote will be dictating the direction of what? Direction of, yeah, the direction of this. So what you need to draw is, you don't need to be so accurate in that. You can just start like this and make parallel in this way. Okay, it will be parallel to this. Now similarly it must look so just like the mirror image. Similarly you may draw like this, so parallel to this. Okay, so this is how this should look like a same, or the mirror image. But the point is, why we are not emphasizing about the accuracy of this drawing, because one of the important thing is these two poles anyway, the direction is shown by this asymptote. So this will be going in this way, That means this particular poles, that is this poles residing at minus 6 and 0, is not going to cross this imaginary axis. So for us, the accuracy is not important for this drawing, because it never crosses this imaginary axis. As long as it never crosses the imaginary axis, and we can conclude here that from this graph that minus 6, the poles due to 0 and minus 6 will not affect or will not aid or will not cause the instability for the system. Now, if there is an instability, then that may be only due to these two complex poles, and that we will see in the next session. So okay, so due to these poles, no chance of the system going into instability. Next step is step number 8. I'm going to introduce a term called as angle of departure. Now, along with this, you can also find another angle called as the angle of arrival. If there is an angle of departure, then you will be having an angle of. Okay, so this is the angle of departure of complex poles. Then the angle of arrival has to be for complex zeros. Okay. So these are the two terms associated with complex poles and complex zeros. Do remember, it is the angle of departure is the term which is associated with the complex poles, while the angle of arrival is called as the complex zeros. And the thing is very simple. You know the meaning of departure, right? Now these two complex poles, anyway, as we have studied that the root locus starts from this pole, just as it started from these two poles, right? And that means this root locus departs. Now the question is, if one departs from this point, I mean there must be a reference point of departure. Say this particular pole can depart at this angle, or this angle, or this angle, and so on. That is, so I'll just explain. Say suppose you have a pole over here, and this is the reference point. Now this particular pole can depart in this way, or it 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 can depart in this way. Okay, so there are different angles of departure. Now instead of this, if you consider a zero, a complex zero. Now what is the nature of a zero? Zero won't depart, right? Now somewhere from the roots will be arriving at a zero, right? Now a root can arrive at this angle with respect to this real axis. It can arrive at this angle, this angle, this angle. Okay, so this is the meaning of angle of arrival. This is angle of arrival. So this is it. So this is angle of departure. This is the concept of angle of departure, and this is the angle of arrival. Okay, so in our problem you don't have to consider about this because we only have complex poles. So wherever there is complex poles, that complex poles will depart from the real axis at a particular angle called as the angle of departure. Okay, now the angle of departure is given by the equation. Okay, the angle of departure is given by the equation is given by, okay, so let us call that as phi. Phi is given as 180 minus the sum of phi pi minus the sum of phi zi. Okay, I will explain what it is by a picture. Okay, now consider a scenario like this. You have 4 poles and a 0. Okay, so you can have a transfer function like this, open loop transfer function. So these are the open loop poles, 2 real poles and 2 complex poles and a 0. Now the meaning of, now I am going to, our consideration is, we will be considering this. We want to find out the angle of departure of this pole. Okay, now our concern is how this complex pole departs. Now in order to measure this, we want to get the idea about this. What is this? This is actually the angle made by the other poles and other zeros to this. Okay, that is the angle subtended by the other poles and zeros other than this to this particular pole. Now if you will be getting those angles and take the sum and put it into this equation, you will get the angle of departure. Right. Now how to calculate that? Now this is a 0, this one is a pole, right? So what you need to do is always the angle is measured in this is to be taken, this is the anti-clockwise direction, so the angle will be taken in the positive direction. Now what is the angle subtended by this particular pole? So for that, what you need to do is draw a line joining these 2 points. Okay, right? So it will be nice if you plot that in a graph. So you can also use another graph sheet to find out the departure, or you can use the same sheet where you are plotting the root locus if there is a space somewhere below the root locus plot, okay, in your exam. So there's no problem in doing that. So you need to show that. That's very important. Okay, so you can measure this angle. So anyway, my suggestion is always go do that in your graph sheet. Okay, just as you have plotted this root locus, somewhere or other, just draw a graph and mark all these poles and zeros if there is. Then now how will you find out the, so this is actually the so-called, this is P1, this is P2, this is P3, and this is P4. Now we want to find out the angle of departure corresponding to and I'm calling this the net angle that is obtended by this as phi. Okay, phi, right? So this is the angle phi P1, or the angle contributed by pole P1 on P4, right? So similarly, you may draw a straight line joining these 2 poles, okay, and always using the protractor you can measure this angle. So call this as phi P2. So do remember, you need to take the measurement from the right of this pole from the real axis in the anti-clockwise direction. Then only you can take this as positive. So similarly, what about this? This is the reference. With reference to this, anyway, this complex, the conjugate of that will be always 90 degree. Okay, you don't have to measure that even. So this is anyway 90 degree, right? So this is actually your phi P3. Now you need to find out one more, then that is actually, let us denote that as a 0, Z. Now this is the contribution by 0, right? Okay, call this as phi Z. Now how to calculate this? Using this expression you can find the phi, or phi is actually the angle of departure, okay, by what? By P4. You are actually finding out the angle of departure by P4. Now that is given by 180 minus the sum of the angles of what? Angles subtended by the 3 poles, that is phi P1 plus phi P2 plus phi P3, okay, minus the sum of the zeros. There is only one zero, so you just need to minus this phi Z. Otherwise you will be subtracting this, the sum of the angles subtended by zeros. So hope this is very important. So in different textbooks you will be having some, there may be there may not be a bracket, so don't get confused by that. Just follow one thing. So this is 180 minus phi P1 plus phi P2 plus phi P3. Okay, so this is angle of departure. Now similarly, say the same scenario, I'm considering the same scenario. Now the difference is I have a complex 0. Okay, now if I have a complex 0, I told you earlier that that must be an angle of arrival, right? So that means one of these poles will be coming over this and one of these poles will be coming at this. because whenever there is a 0 present near any one of the poles, one of those poles will be terminating at any one of those zeros. So you have two poles and two zeros here. Definitely among these three, we are not sure which will go to which side. Anyway, among these three, two of these poles will be terminating at these two poles. So that means the pole has to, the locus has to come from this pole and arrive at this zero. So you need to find out this angle of arrival, and I'm again calling this as, the only difference is the procedure is same. You need to draw the line, straight line, find out the angle in the anti-clockwise direction. Here also draw this line, take the only difference is 180, okay, 180 plus 180 plus the same thing, the sum of 5p minus sum of 5z. Okay, the only difference is just add a plus and do the same expression. It is sum of poles minus sum of z. That is the 5 due to 5 of the arrival. This is arrival, this is departure. Okay, hope you understood. So in this case, in our problem, what you need is angle of departure. Okay, so look at this. So you have a complex pole, so you require an angle of departure. For that, it will be nice to find out. You don't make this picture so you need to present this very neatly. So my advice is always find out the angle of departure in a separate graph or in a part of this graph paper. If you have space for this graph paper, just draw this and find out the angle of departure separately from your graph. Don't try to find out from this, so that becomes so messy, and the examiners may not be able to view your real root locus. So present your root locus in a much presentable way, so that as far as possible all the calculations has to be done as I told you earlier. To solve the characteristic equation, if you want the graph, do it separately. Similarly, angle of departure and angle of arrival may be found out separately. Now the next question is, sometimes, so I will be getting, say for example, I will be getting a 5. Now if this is a positive 5, what you need to do is take this 5, okay, and this plot this root will start in this angle, okay, right? Now the question is, this will be moving and it will be crossing this imaginary axis. Now we want to know whether the root locus crosses the imaginary axis. That we studied in the last class, how to find out the imaginary axis point. Take the characteristic equation, apply root locus to find out whether it crosses the imaginary axis. Okay, so that's it. So whenever it crosses the imaginary axis, one of the rows is going to be 0. That's what we studied previously. So here also, in the next step, that is in step 9, we'll be finding out the intersection of the root locus on the imaginary axis. Okay, now we know that if we have already proved that these two poles will never cross this imaginary axis. That means if this root locus crosses the imaginary axis, then that will be due to these two complex poles. That's what we are going to find out next. Okay, how to find out the angle of departure. So I have just again redrawn in a separate graph the pole zero plot as shown here. That is at -2 plus 3j, -2 minus 3j, you have a complex pole. You have a pole at 0 and at -6. Now how to find out? The first thing, as I told you, join the line, join the points of the poles corresponding to the point of the pole of concern. So this is the pole of concern. This is whose departure we need to find out. So join these two poles by a straight line and find out this angle using the protractor by keeping over here. Okay, and always do remember, take the anti-clockwise direction. So you can see that this is 123.6. Similarly, join these 2 points from the real axis towards the anti-clockwise direction, so you will be getting positive 36.86, and this you don't need to measure because this will be always 90° from the real axis. So always from the x-axis, from the real axis, you need to measure the angle, and you will be getting this much angle. So what is the expression for angle of departure? This is phi is equal to 180 minus, right, 180 minus, you need to take the sum, these are all the poles, right, you need to take the sum of these 123.6, so this will be 123.6 plus 36.86 plus 90, because all these are poles. You need to take the sum of this and you need to subtract from 180. Okay, so you will be getting your answer as minus 70.46 degree. Okay, so this is minus 70.46. Now coming to this root locus here, how will you represent this minus 70.46? How to find out this? So this is your real axis. Now positive angle is taken as in the anti-clockwise, so minus 70 you need to measure in this way. So you need to keep your protractor here, right, and 70.6. okay, 70, the angle is actually 70.46, so you need to mark somewhere over here, and this angle, okay, so this angle you can have a just, so always try to use very light pencils to mark all these things. So as I told you, always your root locus has to be projected. So root locus has to be drawn in the dark lines. So this is your angle, right? Now this is how it departs. So this angle is minus 70.46. Now do I need to find out the departure angle of departure? So there will be angle of departure for this pole as well. Now you don't have to measure this. So this is actually the departure for minus 2 plus J3. Then what about the departure angle for minus 2 minus J3? Since this is the mirror image of this will be plus 70.46. okay, so what you need to do is similarly measure this 70.46 over here. So this is 70.46, right? Okay, 70.46. so measure over here, so you'll be getting a, okay, when you join this you'll be getting a graph like this. So this is the departure angle. So mark this as 70.46. Now the question is, this particular root locus will be meeting, maybe meeting on this imaginary axis. Now that can be found out by applying root locus. So that will be shown as follows. That is your step 9. Okay, so here is the root locus RH criterion to the characteristic equation. So this is your characteristic equation. Okay, obtain this, all these things you know. Now applying this Routh-Hurwitz criterion over this on this column. So everything is positive. So for this to be positive, the condition is 78 minus 0.34, k is equal to 0. From this you may find out the k value. We'll be getting this as 229.4. okay, now how to find out the intersection point? Now when you put k is equal to 229, this row becomes 0. All the rows become 0, proving that this is actually the point of, or this corresponds to, or proving that the root locus at this k will be meeting the intersection point. So how will you find out the point? So when k is equal to 229.4, you can make this row to 0. That means you will be getting the auxiliary equation. So you can write the auxiliary equation for the row just above that. That is, this will be 29.2 s square plus k is equal to 0. Okay, now from this you can substitute k, the value of k to be 229.4. so from this you can find out s, and s you will be getting this as, you may do that by yourself, j 2.98. so you got 2 points, that is minus j 2.98, right? So 2.98 is a point over here, it's something closer to this. This is minus 2.98, and this is minus j 2.98, this is plus j 2.98. so this is how the, look at this, this is how the, this must be the way in which it goes like this. Now you can go, now what is this asymptote? This asymptote suggests then after this root locus has to go parallel to this. Now similarly, what about this? This will be moving exactly in the mirror image. Okay, you can go parallel to this asymptote. So this asymptote, these two asymptote, that is 45 degree and 350 degree asymptote, will be leading this complex pulse, right? And it will be going into this way. So this j plus or 2.98 at this point, what happens? That is at k is equal to 229.4, the system becomes marginally stable, or the root locus meets the intersection point. Now what happens if k becomes greater than 229.4? Then the system, then one of the roots will be, two roots will be going into the left half, proving that the system is going to be unstable. So as far as a designer is concerned, he can design the system to be within the forward path gain of 229.4. okay, so you must make sure that the designed forward gain value must be within this value 0 and 229.4, otherwise the system can go to an unstable state. So this will be giving a more of a time domain response of a system. So basically this approach, even though this is a graphical method, this can be considered as a time domain approach. Okay, now one more point is, we have used this 180 minus this thing. You may just go through this. You got this from the angle condition of root locus. So you don't have to go for the details of this, how you got this and all those stuffs you don't have to know, but you should at least understand that this formula is derived from the angle condition of root locus. We usually find, see, if you want to find out the point corresponding to k, what we do is we make use of the magnitude condition of root locus. Now in the case of angle of departure and angle of arrival is found out by applying the angle condition of root locus. You may just go through that angle condition, which we have studied in the which we have dealt in the first part of this root locus video. Okay.